I welcome you to lecture number 5, where we are going to look at the beginning of fluid dynamics. So all along we've been looking at static fluids. In lecture number 5, lecture number 6 going upwards, we'll be dealing mainly with fluid dynamics. So for fluid dynamics, which means we are going to use some of the energy or most of the energy from the flow of the fluids to generate power. For example, when you are working with wind turbines, working with hydraulic turbines, we are going to use the flow of the energy, because when the fluid is flowing, it possesses some energy that is there. So we are going to extract that energy to change it into some other form of energy that we can use, maybe mechanical or kinetic energy to electrical, mechanical to electrical at the end of the day. So like last time, we defined fluid dynamics as the analysis of fluid in motion. And there's another definition that I gave you that we'll be looking at the fluid in motion, taking into consideration the forces and the pressures that have made this fluid to flow or to acquire acceleration and velocity. So before we go any further, there are some classifications of fluid flow that we looked at last time. It should be lecture number 1. We talked about uniform flow, non-uniform flow, steady and unsteady flow. So these are the things that we still need to go back to understand, so that we are able to solve most of the problems. So if we've got a uniform flow, what it means is velocity, pressure, cross-section, depth are the same at every given point. Then for non-uniform flow is the opposite of uniform flow that we have. Then steady flow, which means what we are looking at is change with time. So steady flow, it does not change with time, and steady changes with time. So all those things we need to put it in mind. Then there are some other scenarios where we can combine both steady, uniform. So which means if it's steady, it does not change with time, and also the flow is constant at any given position. Steady, non-uniform. So which means you have to look at steady as in relationship to time, in relationship to position. Then we've got also unsteady, uniform. So unsteady changes with time, but uniform, the conditions are the same at every point. Okay, so we need to make sure that when you combine all these flow characteristics that we have, understand what you are dealing with. Steadiness has to do with the time. Uniformity has to do with the every point, like the position that you are looking at. Okay. Then last time also we talked about compressible and incompressible flows. So we said for compressible flow, density changes with pressure. Your density changes for compressible flow. Density is not constant, it changes. For incompressible flow, the density is constant. Then we also talked about 3-dimensional flows, where we say that flow can be in 3 dimensions. If it's a Cartesian point that we have, it's in X, Y, and Z. Okay, so which means if it's 3 dimension, this flow that we have has capabilities of flowing in 3 dimensions, which is X, Y, and Z. Okay, so now to simplify our calculations, we are going to look at flow that is steady, flow that is incompressible, flow that is 1, and maximum 2-dimensional flow. But in most of our calculations, we are just going to look at steady, incompressible, and 1-dimensional flow, just to simplify our calculations. So for 1-dimensional flow, if we look at flow in a pipe, we can consider it to be 1-dimensional. Then if we've got a weir that we have here, we can consider it to be 2-dimensional flow. So which means when you look at flow over weirs, put in mind that most probably you are going to be looking at 2-dimensional flow that we have. But flows in pipes, basically it's just going to be flow in 1 dimension. Okay. Then the other thing that we need to define is what are streamlines and what are stream tubes. So streamlines, these are lines that join points of equal velocity. Then they are known as streamlines. So if we draw this line around this body that we have, which means we are going to get a streamline. So along this line, the velocities are the same. Along this line, they are the same. Okay. Then when you look at steady flow, the position of streamlines do not change. Then for unsteady flow, the position of the streamlines, they change with time. Those are the other things that we need to do, to put in mind. So if you are asked to draw streamlines for unsteady flow, put in mind that the streamlines for unsteady flow, they are going to change with position with time. And for steady flow, the position of the streamlines do not change. Okay. So like what I say, that we are supposed to also define what is known as stream tubes. Stream tube is defined as a combination of streamlines. So when streamlines make a tube-like shape, they are known as stream tubes. So we've got a streamline here, streamline. Then when they form something which is almost like a tube, we call them stream tubes. Okay. So the walls of stream tubes are streamlines. And the other thing that you have to put in mind is fluid cannot flow across streamlines. So fluid cannot cross a stream tube wall. Then a stream tube is not like a pipe. Its walls move with the fluid. Then in unsteady flow, tubes can change with position, like what we talked about. And in steady flow, position of stream tubes do not change with time. Okay. So now let's come to some calculations. So for the calculation that we are going to look at in fluid dynamics, we first need also to look at some definitions that we use the most. First one is what is known as mass flow rate. So mass flow rate can be defined as mass over time taken to accumulate this mass. So the symbol that we use for mass flow rate is m dot, which is equal to dm over dt. Okay, so for example, if you want to find the mass flow rate, given that the weight of the fluid is 2 kgs and it's flowing at 7 seconds, and we've collected some water which is 8 kgs, so what would be the mass flow rate? Here we've got the mass, 8 kg is the mass of the water in the bucket, and the empty bucket is 2 kg. So for us to get now the mass flow rate, we just do simple mathematics, which is the total mass minus the mass of the bucket for us to get the mass of the fluid, divided by the time it takes for us to get this mass of the fluid. So when we divide, we are going to get 0.857 kgs per second. So the units for m dot are mass per second. Then the next one that we are going to use also is known as volume flow rate, or the name that we are going to use the most is discharge. So for discharge, we can define discharge as volume of fluid divided by time. The symbol for discharge is Q. So in fluid dynamics, when you see Q, you know that this one is capital letter Q is discharge. And those who are doing heat and mass transfer will also know that when we've got Q, it's a different notation again that we are going to use. So put in mind, for heat and mass transfer, we also use Q for heat flow. So put in mind that now, if it's fluid dynamics, the Q that we have is discharge. In heat and mass transfer is heat flow rate that we will be looking at. Okay, so now if you want to find the discharge for a bucket that was filled with 2 liters of water in 25 seconds, so which means what you need to do is first convert these liters to meter cubic, which is SI unit for volume, and divide by the seconds that we get. Then from there you can get your answer as 0.008 meter cubic per second. So for discharge we use meter cubic per second, or sometimes liters per second, but we always use the SI unit, which is cubic meters per second. So also know how to convert liters into cubic meters. These are the basic definitions that we use again: mass flow rate and volume flow rate, known as discharge. Okay, so for us to find the discharge and mean velocity, we can look at this analog that we have here, that in time t, a cylinder of fluid which will pass point X with a volume of A multiplied by u multiplied by t. So which means there's a flow that is coming this direction. At this point x, we are going to get at time x, at time t, a cylinder or fluid will pass through point x with a volume of a multiplied by u multiplied by t. So where are we getting a multiplied by u by t? We know that when we are calculating volume, volume is equal to area multiplied by height. Area multiplied by height. So with that height, if we say height over time, then we multiply by time here. Height h over time, then we multiply again by this time. We are going to get a multiplied by h over t multiplied by t. So in other words, we have not changed anything. Okay, let me start again. Volume is equal to area multiplied by height. So volume of a cylinder is equal to area multiplied by height. But here we don't have height. We want to replace height to involve velocity in this case. So how do we do that? If we say area multiplied by, for us to get velocity here, velocity is equal to what? Velocity is equal to distance over time. So if it's distance, distance over time, and our h, we've got h is the distance. So we can write a multiplied by h over time. So for us not to change anything, we are supposed to multiply again time here, so that we don't change anything. You can try it when you're home. Just try to replace u with distance over time. You see time and time will cancel and we'll get area multiplied by distance. And our distance in this case is height. Okay. So we'll write this one as volume is equal to area multiplied by velocity multiplied by time. So now if we come back to the definition of discharge, discharge is equal to volume over time. So in other words, we can write volume is equal to a multiplied by velocity multiplied by time over this time that we have. Time and time cancel. So we are going to get q is equal to a multiplied by the mean velocity. Take note of this. Discharge can also be defined as area multiplied by the velocity or the mean velocity that we have. Okay. So here's another example of how to find the mean velocity when you are given the area in the discharge. You can take a look at this during your spare time. Okay. So we'll come back again to that equation that we have looked at, which is q is equal to a multiplied by velocity. So one of the laws that we are going to use the most again is continuity equation. So for continuity equation is defined as the mass entering per unit time should be equal to mass leaving per unit time plus the increase of mass in control volume per unit time. Then since we say that in this course we are going to look at steady flow, incompressible, and one dimension. So what we are going to look at now is if it's steady flow, this equation will simply reduce to mass entering per unit time is equal to mass leaving per unit time. So if you are going to involve now equations, which means mass entering per unit time, this side will be rho 1 change in area multiplied by velocity should be equal to rho 2 change in area multiplied by velocity. So for steady flow only, we have got rho 1 change in area multiplied by u1 is equal to rho 2 change in area 2 multiplied by u2, which is equal to a constant. And this constant, since we are dealing with mass entering per unit time, mass entering per unit time is defined as dm over dt. Okay. So this equation is known as the continuity equation for steady flow. Now, when we include the other part, which we are saying that the flow is incompressible. So what it means that if the flow is incompressible, rho 1 will be equal to rho 2. Rho 1 will be equal to rho 2, like what we can get here for incompressible flow. Rho 1 will be equal to rho 2. So if rho 1 is equal to rho 2, then rho 1 and rho 2 can cancel. And we are going to get A1, U1 is equal to A2, U2. And from the previous definition of discharge, we said discharge can be defined as area multiplied by area. Multiplied by velocity, sorry. Area multiplied by velocity. So in this case, we can get A1 U1 is equal to A2 U2, which is equal to Q. And this is the continuity equation that we are going to use the most, since we say that the flow is going to be steady and incompressible. Okay. So now, these are some of the examples for continuity equation where we have got flow coming from a larger section to a smaller section. So in this case, we expect that the velocity will be lower than the velocity at this point. Why? The area is larger and this area is smaller. So for us to get A1 U1 equal to A2 U2, we are supposed to get larger area here correspond to smaller velocity, or lower velocity. Smaller area corresponds to larger velocity. It's like when you are irrigating or you are using a hose pipe to water the garden. For you to get a larger velocity, you have to put your finger in front of the hose pipe so that you can get a smaller area. Smaller area, we see your water will go further because it's now having higher velocity. That can be one of the examples that we can look at. Okay. So, similarly, when you've got water coming from smaller pipe to a bigger pipe, so which means we've got higher velocity, and this side you are going to get lower velocity. So when you do your calculations, if you find the velocity here it's lower than the velocity in section 2, then just know that you have made some errors and your answer is wrong. Under normal circumstances, we've got a smaller area should correspond to higher velocity, and larger area should correspond to lower velocity at the end of the day. Okay, so now if you've got velocities in a pipe from a junction, so we've got velocity like flow coming from point A or point 1, and it reaches a junction where it goes to 2 and 3. So what we need to know is mass flow into the junction should be equal to mass flow out. So whatever is coming in should be equal to whatever is going out. So in this case, we will look at Q1 should be equal to Q2 should be equal to Q3. Same here, when you've got mass flow, 2 points, you've got the mass flow entering in and 1 point is exit. So what we look at is this Q1, the output should be equal to Q2 and Q3. Okay. So this is another example that we have that we can take a look at how we can apply what we have learned to solve the problem. Like in pipe 1, diameter is equal to 50 millimeters, the mean velocity is 2 meters per second. Then pipe 2, we have got diameter 40 millimeters and takes 30% of total discharge, and pipe 3, diameter 6 millimeters, 60 millimeters. What are the values of discharge and mean velocity in each pipe? So we need to look at this equation that Q1 is equal to this, Q2, Q3. Then from there we equate them. Say like you need to consider which ones are the inlets and which one are the outlets. So inlet should be equal to the outlets. Then when you solve your problem, you get that Q1 should be equal to Q2 plus Q3. But in this case, what we want to find is Q3. So we'll make Q3 the subject formula to find the velocities at point 3 and also point 2. Okay. So from there, this takes us now to the famous equation, which is the Bernoulli equation. So Bernoulli equation is written as pressure energy per unit weight plus kinetic energy per unit weight plus potential energy per unit weight should be equal to total energy per unit weight. Please take note of this definition, because if you are asked to derive Bernoulli equation, if you don't know this part, you won't be able to derive Bernoulli equation. So you need to know that pressure energy per unit weight plus kinetic energy per unit weight plus potential energy per unit weight should give us the total energy per unit weight. So when we play around with figures and change this pressure energy is equal to what? Mg. So if you come back here to where we are going to derive potential energy is equal to mgz. Then kinetic energy is half mu squared. Then pressure energy is equal to rho gh. So we are going to use pressure energy, which is rho gh. So when you play around with those equations, you are going to get pressure 1 over rho g plus u1 squared over 2g plus z1 should be equal to a constant. So we define these terms as rho 1 over p1 over rho g is known as the pressure head. Then u squared over 2g is known as the velocity head. Then z is the potential head, and h will be the total head. So if we are talking about the head, so which means the units that you are going to get from here are meters. Since we are looking at the head is measured in meters, like how we defined head last time. That is the vertical distance that we are looking at. So if it's distance, then which means our measurements of the head should be in meters. Okay, so there are some restrictions that are there in application of Bernoulli's equation. So number 1, the flow is supposed to be steady. The flow is supposed to be incompressible. The density is supposed to have incompressible flow, which is the density is constant. Friction losses are negligible, etc., etc. All these are the limitations that we have on how to use Bernoulli equation. So if there is heat transfer and there is shaft work and there is friction, the flow is unsteady, we will not be able to apply Bernoulli equation. We can only apply Bernoulli equation when these conditions are met. Okay, so bringing you back to this part, it shows how to derive Bernoulli equation. So like what I was saying, for you to derive Bernoulli equation, first thing that you need to put in mind is to know that pressure energy plus kinetic energy plus potential energy will give us the turnout energy. Then from there, we can follow these steps to come up with P over rho g plus u squared over 2g plus z is equal to h. Okay. So now, when we've got 2 points, so we will know that the Bernoulli equation that we have, or the total head that we have here at 1, should be equal to the total head that we have at 2. So for us to find the total head, we have to use the Bernoulli equation, which is this one at point 1 should be equal to this Bernoulli equation at point 2. Then when we've got losses or losses that we have, we can put them as in form of H, W, and Q. So which means anything that takes away energy from the system, we put it to right hand side. So which means losses, if there are losses, we are going to assume energy losses due to friction and all these from the pump and everything that we have to put them to right hand side of the equation that we have. Then anything that adds energy, we put to left hand side. Okay. So what we need to put in mind now is, here we're looking at Bernoulli equation in terms of the head. So if you want to look at Bernoulli equation in terms of pressure, we can say pressure, which is static pressure, plus dynamic pressure, plus this one is the common pressure that we've been looking at in statics, is known as hydrostatic pressure, should be equal to a constant. And this is only true if you put those assumptions. So before you write Bernoulli equation, please put the assumptions. The assumption that the density is constant. Then the other assumption is what? Yes, steady flow. Other assumption is what? Yes, one-dimensional flow. So here, even if we say U1 and U2, it's still one-dimensional flow because we are looking in the U direction. So if it was two-dimensional flow, we're going to look at U and V. But so since we are looking at U1 and U2, this is still one-dimensional flow because it's still in U direction, which is X direction. Okay. So the total pressure that you are going to get is the summation of static plus dynamic and hydrostatic pressure. which means that if you don't include the assumption that the flow is steady and the flow is incompressible, the equation that you are supposed to write is this one, which is integration of dp over d rho plus integration of dv over dt ds plus v squared over 2 plus gz is equal to constant. So it's very important that when you are answering the question, always put the assumptions, include the assumptions. Without assumptions, your answer can be marked wrong. So now let's look at some practical application of Bernoulli equation. So for us to apply Bernoulli equation, let's say we've got this problem that we have. We've got point 1, section 1 and section 2. So in this case, we want to calculate for the unknowns. So in this case, we want to calculate the gauge pressure in point number 2. What is the gauge pressure here, given the other variables that we have? So we know that the total pressure at 1 should be equal to total pressure at 2. Total pressure in section 1 should be equal to total pressure in section 2. Or total head in 1 should be equal to total head in 2. So we use this equation, Bernoulli equation for 1 and Bernoulli equation for 2. We make P2 the subject formula. Then from there, since we don't know the velocities for point number 2, but we are given velocity for point number 1 and area for 1, so we can use now the continuity equation to find velocities at 2, so that we can bring it back to this equation to solve our problem. So most of the time when you are working with the Bernoulli equation, you also need to use continuity equation in most cases, because if you don't know the other velocity here, but you are given the velocity in section 1 and the diameter or the area for section 1, you can use the continuity equation, which is a1 u1 is equal to a2 u2, to calculate the unknown, which is u2. Okay, then from there you've got now a simultaneous equation that you have that you can solve to calculate your P2. Okay, so those are some of the applications that we have. Then we can apply Bernoulli equation in pitot tube, which means we have got section 1 and section 2. So for section 2, we have got what is known as stagnation point here, which is point number 2. So point number 2, stagnation point, what it means is the velocity at 2 is equal to 0. Then they are in the same horizontal plane, so which means we've got Z1 is equal to Z2. Then from there, we can now find the pressure. We know the pressure at 1 and pressure at 2. Pressure at 1 is ambient pressure, at atmospheric pressure. So we can find now the pressure at 2. Then from pressure at 2, we can find our velocity, also using this equation. Make velocity the subject of formula. Okay, then the other thing that we can do is we can use piezometers to work with our pitot tube. So we can connect this zone number 1 to this part, which is subjecting pressure here, so which means it's pushing pressure down this side, and zone number 2, which is ambient pressure that we have, it's also being subjected this side. So this X that we have now, using the equation that we worked with manometers in statics, we can find this increase or this pressure that we have here using manometer. So if we work with manometers, we can find also our U1 using raw manometer that we have here. So the advantage of using a pitot tube is simple, gives velocities, and the other disadvantage that we have now, so which means the major advantage that we have is simple to use and analyze, but its setbacks is it only calculates velocities. We can't use pitot tube to find discharge, and may block easily. So for those who are doing aeronautical engineering, we work with a lot of pitot tubes in aeronautical for calculating velocities of an aircraft, etc. So the other setback that you can have with pitot tubes is they can block easily. Now when they block, they can cause harm to aircraft. There are some aircraft incidents and accidents that have happened due to the blockage in pitot tubes. So it can be a setback again and cause some distraction. Other use of Bernoulli equation, we can use it in venturimeters. So for a venturimeter, which means what we want to find here and calculate is to calculate the discharge. That's what we want to do here, to find the discharge. So we can work with section 1 equal to section 2. Then the other thing that I say that we will also need to use continuity equation to find the unknowns. So when we impute these in the equation that we have here to find u2, we can get u1 is equal to a2 square root of all these terms that we have here. So what we are getting here, don't be scared, is just a matter of simply substituting in this equation. So we've got simultaneous equation where we need to find u1. So after getting u1, we need to find the discharge. We'll come back to this equation. Q is equal to u1a1. So we know that discharge is equal to velocity multiplied by area. But now we've got what is known as ideal discharge and also what is known as actual discharge. So for ideal discharge, here we are not considering any losses. So which means for ideal discharge, Q ideal will be equal to U1 multiplied by A1. But now for actual discharge, we need to include what is known as coefficient of discharge, which is CD. So it will be CD, which is approximately equal to 0.9, CD U1 A1. So we have already calculated U1, and U1 is given by this equation here, which is A2 square root of 2G P1, all these terms that we have here. So we can find now our Q actual being equal to CD A1 A2 multiplied by this term that we have. Okay, so still on CD is coefficient of discharge, and there are some other coefficients that we are going to look at further, which is CC, CV, and also another CD, which is coefficient of drag. So coefficient of discharge, we normally use it for internal flows. Then coefficient of drag, we use it mainly for flow which are external flow. So if you are asked to differentiate between coefficient of drag and coefficient of discharge we use it for external flows. Coefficient of discharge we use it for internal flows. Then coefficient of drag we use it for external flows. Coefficient of discharge, internal flow. Coefficient of drag, external flows. Okay. So for venturimeter design, you can go through these manuals that we have, how to come up with a venturimeter design. Then the next one that we have is flow through small orifice. So for flow through small orifice, we've got a tank here. So we know that this one is open to ambient air. So this water or liquid that is here is coming through this orifice. So it will form a jet of fluid that we are going to get here. And at this point, we've got what is known as the vena contractor. So the contraction that we have here is known as vena contractor. So from there now, we need to find the velocities at the vena contractor, what we are going to get. So we know that velocity at 1 will be equal to 0 because it's not moving. Then pressure at 1 is equal to 0 because it's open to the ambient. Then pressure at 2, which is just a bit away from the opening here, it's also atmospheric pressure that we have. So which means pressure at 2 is equal to 0. So if you work with Bernoulli equation, which is P1 over rho G plus U1 squared over 2G plus Z1 is equal to P over P2 over rho G plus Z U2 squared over 2G plus Z2, we'll simply get an equation which is H is equal to U2 squared over 2G. So our U2 in this case will be square root of 2GH. Then for us to find the discharge, we have to multiply this by area. So before we calculate the discharge, we need to find what is known as the actual velocity, because at that vena contractor we are going to get some friction losses that are going to be there. So the velocity might not be the actual velocity that we will get. So the actual velocity that we are going to get, this one U2 is equal to square root of 2GH, is ideal velocity. But now due to friction losses, we need to also find the actual velocity, which is CV, coefficient of velocity, multiplied by the U theoretical or multiplied by U ideal. So this one can be known as theoretical velocity or ideal velocity. So each orifice has its coefficient of velocity, which is different. So most orifices the range that we have is between 0.97 to 0.99. Of course, some other literatures, they give this range a different range for this coefficient of velocity. Okay, so now the other thing that we need also to look at is the actual area. So actual area will be equal to coefficient of contraction multiplied by area of the orifice. So now to get the Q actual, we need to multiply the actual area multiplied by the actual velocity. So which means actual area is CCA orifice. So which means this CCA orifice will give us the actual area. Then the actual velocity, we need CV and U theoretical. So CV, U theoretical will give us the actual velocity. So what we can look at now here is CC multiplied by CV gives us what is known as CD, which is the coefficient of discharge. So in other words, we can find actual discharge equal to CD multiplied by a orifice multiplied by square root of 2GH for small orifice. So we have to put in mind that CD is equal to CC multiplied by CV. Then the next thing that we will need to do is to find the time that it will take to empty the tank. The time that it will take for us to empty the tank. So from there, we've already calculated and we managed to find that Q is equal to CD A naught multiplied by square root of 2GH. So how long is it going to take to empty this tank? So this now will bring us to differential equations, and you need to know some integration and some calculus. You need to know more of calculus in this topic for you to solve it. So here what we are going to do is, we know that Q is equal to A multiplied by U. Okay, then we can remove this U. We know that U is equal to distance over time, so we can write Q is equal to negative A multiplied by distance over time, H over T here. So we have put a negative A or a negative H. This negative represents that this H is falling, so which means this H is reducing. When we are emptying a tank, which means this volume or this H is reducing until it comes to this point whereby it's empty. Okay, that's why for this negative sign that we have here. So Q will be equal to negative A dH over dt. From this equation that we have, Q is equal to A U. U is distance over time, so there's nothing that we've changed here. But now we come back to our equation now. We know that Q for an orifice is this one, CDA square root of 2GH, should be equal to this part that we have, A dH dt, what we have here. We make T the subject formula because as we are interested in finding the time. So T the subject formula, divide by this term throughout and play around with some terms, we'll get dt is equal to this part that we have. Then we integrate both sides. So here we are integrating in relationship to T, this side we are integrating in relationship to H. So if you are integrating in relationship to H, A CD A naught square root of 2G, this one becomes a constant. The only thing that is varying is H, because H is reducing. So we need now to integrate integration of 1 over square root of H. Please go and learn your integration very well, because without learning your integration, this part will be very complicated for you to learn. Go and learn the basics of integrations. Okay, so what we have done here, let me take you back again. We started with Q is equal to A U. So we know that U is equal to distance over time, and we know that the H is falling, so we need to introduce a negative sign here. So we are going to get Q is equal to negative A dH over dt. Okay, but now we know that Q for an orifice is given by CD A naught square root of 2GH. So we substitute Q here to get negative A G change in H over dt. Then from this equation, we are going to get our dt is equal to this part, so that we can make T sub your formula, since we want to find the time that it will take to empty the tank. Okay, then from there we find T. And for us to find T, we integrate both sides. When we integrate this side, we get T. Integrate this side, we are integrating relationship to H, because the other ones we are going to take them as constant. As constants. Okay. So here we are integrating from H1 to H2. So H1 is the initial point, H2 is the final point that we have. Then when you do our calculations, which means the time that it will take to empty this tank, it will be equal to negative 2a over CD a naught square root of 2g multiplied by h square root of h2 minus square root of h1. Okay. Then now, the other thing that we can do is, what time, if we've got two tanks, how long will it take to equalize these two tanks that we have? We still come from Bernoulli equation from point 1 and point 2. So point 1, P at 1 is equal to 0. Velocity at 1 is 0 again. So we are just remaining with this H1 that we have. This side, what we have? P at 2 is 0. No, P at 2 is not equal to 0 because we are looking at this point. So which means what we have is rho G H2 over rho G plus U2 squared over 2G. So we are looking at point at this point here. Point number 2. So it's not equal to 0. Our pressure at 2 is not equal to 0. Then Z2 is equal to 0 because this one is the point that you are looking at when they are going to equalize. Okay. So U2 will be this formula that we have. Then CD, then our discharge that we are going to get is CD A naught 2G H1 minus H2. So if we look at this point, we've got 2G H1 minus H2. The last point, it was just like CD A naught is equal to 2GH. There was no subtraction that was there. But in this case now, we are subtracting H1 from H2 when we are going to equalize these two tanks. So which means this distance that we are looking at from here to there, which is H1 minus H2. Then the rest is the same. We will still come back now to the formula that we said Q is equal to negative A1 D H1, integrate, make T the subject of formula, then find the time that it will take to equalize the tank. Last but not least, let's look at flow over notches and wears. So we still need to work with Bernoulli equation to find the flows, to solve the problems that involve flows over notches and wears. So for a general wear, the equation that we use is given as this part. Please know this equation. I don't usually give it in an exam, so it's something that you need to know by heart. So this is the general equation that we have, that the Q theoretical is equal to 2G square root of 2G integration of 0 to H BH half DH. So if you've got a rectangular wear, we still use this same equation. Then what you are going to get here is this part, Q is equal to 2/3 B square root of 2GH 3 to the power 2. Then if you want to find the actual, we multiply this theoretical by CD. Then if you've got a V notch, our B changes. It's going to be equal to 2H minus H tan theta over 2. Then we still come back to our general equation, which is this one. Then replace this B with this equation that we have. Integrate, you get this part. Sometimes the question will come asking you that show that the actual discharge for a V notch wear is given by this equation. So you need to do all this integration to come up to this equation that we have here. Okay. So in summary, to summarize things that we have learned today, basically you need to know the Bernoulli equation by heart, either by using pressure heads or by using pressure where we've got static pressure, dynamic pressure, and hydrostatic pressure. Okay, then also need to know cases where we cannot apply Bernoulli equation. So if you do those, you are warm and dry, you will be able to answer most of the questions. So for tutorial questions, I will send through your class rep the tutorial questions that we will need to look at. But I urge you to go back to that handout that I gave you, which has got question and answers. Go and try to answer the problems that are there that involves Bernoulli equations and its applications.